Perfect. All right. So let me give you a quick introduction into adhesives and materials for automotive lighting. And for those of you who have not heard of DELO before, I just wanted to give a quick introduction here. So DELO is a company from Germany that here you can see a nice picture from above. So we are a family-owned company and have a revenue of roughly 200 million with 1,000 employees. And why I want to show you this is because we are active in multiple markets. We are known for adhesives for different applications, for example, in smartphones and consumer devices, but also in automotive. And what you can see here on this picture is different parts that we are already having quite a lot of experience in with our adhesives, like in cameras, in displays, in sensors, or in electric motors. And a huge new trend that we can see is in automotive lighting. More and more companies are working on slimmer designs, on new trends, new LEDs being used in here. And this is where we are also active in. And this is what I want to show you on the following slides. And as a quick introduction, oh, that was the wrong direction. As a quick introduction, maybe many of you have already seen this article. It's not the newest one, but here we can see, for example, Reinhard Völker from Swiss Micro Optics, which has recently been acquired by Focuslight, talking about microlens arrays. They have the advantage of a precise light with very tiny lit surfaces, still having issues with lower optical efficiency and a higher price. But it was said that this is becoming a revolution in the lighting technology. And we can confirm that there's a lot of activities on the market here, and this is where we are active. So this technology is on the rise from our side, and this is why we are working on it. And just as a quick reminder, this technology works like, for example, in projection systems, when you have a single lens and a single optical component being projected, you can reduce the distance between light source and the optics by using micro lenses, by using a lot of lenses next to each other, with the benefit of being even smaller. And for this, you need devices like the microlens array, where we have 4 different layers. So we can see the optical material being highlighted in magenta here on top and on the bottom, with the glass wafer and the chromium mask in between. And with this double-sided imprinted lens structure, we can accurately align all those lenses to those optical components in the mask. And this is exactly where we are very active on developing materials for these microlens arrays. And before jumping into our developments, just as a quick reminder how these microlenses are manufactured. So first of all, we have the liquid polymer or the liquid material being dispensed on a glass wafer. In this case, we are just showing the material in magenta just for marketing purposes. So after the dispensing, we have the imprinting, where we have a transparent stamp imprinting the structure of the lenses into the liquid material. And after that imprinting step, we have the curing of the material through the stamp. So we use the transparent stamp to cure it, to cure through the stamp. And after demolding the stamp from the material, we end up with a finished wafer. And after the dicing, we can just dice out bigger areas. So we end up with microlens arrays. And you can imagine that for this process, it's not only important to develop a material that has a good optical performance, but it also needs to perform in the manufacturing process. So this process is very specific. And for this stamp, we are using the same stamp over and over again to be efficient in the process. And this is something we are looking into together with partners. So on the next slide, I just want to show you a little bit our activities in terms of repeatability. So what you can see here is that we are investigating the height of the lenses and also the diameter. Here you can see the values for the master. So for example, in this example application, we can see a master having a height of 90 micrometers and the diameter of 480 nanometers. And in those graphs, we can see the results of the lenses that are imprinted between different machines. So M1 is machine 1. So we tested 5 different machines for both values and also multiple imprints at every single machine. And the result was that the variation within a machine is lower than 1% for both values. and the variation from machine to machine is lower than 2%. And these are quite good values for manufacturing these kind of optical components on a mass manufacturing scale, resulting in these components. So here we can see a microlens array, the final product. And for us, it was very important to highlight how we can improve the machine-to-machine reproducibility, not only focusing on the optical components and the optical properties here. This was in collaboration with SÜSS Microtech from Munich, where we investigated it together. So we are focusing on improving the material, and they've been focusing on improving the process and all the machine parameters. But besides working only on the process, we of course focus a lot on the material requirements itself. So for the automotive lighting applications with the microlens arrays, I think the most important property is the high transmission in the range of the visible light. So we need to be as high as possible, obviously, to transmit all the light and shape it in the form that is needed. The second important requirement is the optical stability. So this transmission has to remain high even after UV radiation, even after humidity, and also temperature storage. So this is where we do a lot of long-term tests to measure the transmission of our optical materials to be as close as possible to the end application in the automotive headlamps. And last but not least, we also checked in mechanical stability, which is very important because with all these long-term vibrations, for example, and the temperature overlay, it comes to stresses in between of those different layers. And this is where we do a lot of mechanical evaluation of those materials being cured in those specific areas and thicknesses. And all in all, in combination with the process, is what we test in order to develop our materials. Let me also jump a little bit into some values here, and I would like to highlight the optical stability. So in terms of optical stability, what you can see here is 4 different products from DELO. So we can see here in the 4 colors, 4 different optical materials that are used in automotive applications in terms of imprinting. And the first group of values shows the transmission at 420 nanometers initially. That means no storage conditions were applied, and the transmission was 100% for all of these. So the initial transmission is very high, but we know from our customers and also from our experience that in these applications, especially the temperature is very important. So what we did was, even though the reflow process is not always necessary in the manufacturing, it shows how the material reacts after a high temperature overlay. So when going 3 times through the reflow process with all of these materials in a layer thickness of 100 microns, we can see that the transmission drops. It goes down, but it remains higher than 95%. So 95% is a little bit of a threshold that we need to be higher. And all of these materials are still higher, but we can see a clear favorite here with the OM6115 being still higher than 99%. And I think the test that is even more relevant for automotive headlamp applications is 125 degrees Celsius. Because in those microlens arrays, we can have quite high temperatures over time, and 125 degrees Celsius is a temperature that we test a lot in. And the newest material still has a transmission of higher than 99%, which is a very good product on the market already. So our current products already show a pretty good yellowing behavior after these aging steps. But what we are currently looking into is still improving these. Even though this is already good, what we try to see is how to improve the transmission after high temperature storage and UV irradiation at the same time. So these are the trends that we can see here. We are working on new products, testing them together with partners, and I can show them to you maybe in the next meetings, but this is a clear trend that we can see here, with these products being our starting point. And in the headlamps where those microlens arrays are used, we see a lot of different bonding tasks as well. So here you can see such a module using a microlens array optic at the top, and this microlens array is often bonded into a housing. So for this housing bonding, you can see the next adhesive being used here in magenta, where we have a different candidate with the OB4189, and also other adhesives being used in these headlamps, for example, for the bonding of the collimating lens or the LED to a heatsink, for example. And for these, we have different products where another team is focusing on. I could see some of my colleagues already also in this online meeting here. But I just want to show you with this that we are working on all the bonding tasks that are relevant in these MLA headlamp applications. And if you have any questions here, feel free to reach out to us. We are very active in testing with our partners together, and we would really like to improve the materials together with you. So feel free to reach out, and I'm looking forward to your questions right now in the chat, or yeah, maybe here in person.